Scene script. Have you ever wondered what makes up the world around us? What is that one fundamental building block of matter? The answer lies in the heart of science, and it is as mind-boggling as it is simple. The atom. This microscopic marvel, invisible to the naked eye, is the smallest unit of matter that defines the chemical elements. Picture this: everything you see, touch, and feel is made up of these tiny particles. The air we breathe, the food we eat, the stars we gaze upon in the night sky, even our very bodies and thoughts, all are composed of atoms. They are the bricks and mortar of the universe, constructing the intricate tapestry of reality as we know it. But atoms are not just building blocks. They are more than mere components of matter. Each atom is a universe within itself. At the heart of an atom you'll find a nucleus, composed of protons and neutrons. Orbiting this nucleus like planets around a sun are electrons, creating a dynamic dance of forces and energy. Atoms are not stagnant, they are vibrant and alive with activity. They interact, combine, and split apart, giving rise to the myriad forms and shapes of the physical world. They are the authors of chemical reactions, the weavers of molecules, and the creators of compounds. In short, they are the silent architects of the universe, shaping and forming everything from the smallest grain of sand to the largest galaxy. Yet despite their importance, atoms remain largely a mystery. They are so small that even the most powerful microscopes can't see them. It's a paradox of sorts. The smallest things in the universe, which we can't even see, make up everything we can see. So there you have it, the atom, a tiny universe within itself, making up the world around us. As we delve deeper into the world of atoms in the next scenes, remember this: every atom in your body came from a star that exploded. You are stardust. You are the universe experiencing itself. But how did we come to know about these tiny particles? It's quite a fascinating story. Our journey begins in ancient Greece, where philosopher Democritus first proposed the concept of atoms. He believed that everything in the universe was made up of these tiny, indivisible particles which he named atomos, meaning uncuttable. But without scientific evidence, his ideas were dismissed for centuries. Fast forward to the early 19th century, and we meet John Dalton. He breathed new life into Democritus's forgotten theory with a scientific approach. Dalton proposed that atoms of a particular element are identical in mass and properties, and that in chemical reactions, atoms combine, separate, or rearrange. This was the first atomic theory backed by experimental data. Not long after, at the turn of the 20th century, J.J. Thomson made a groundbreaking discovery. He found that atoms were not indivisible after all. Using a cathode ray tube, he discovered the electron, a particle even smaller than the atom itself. This marked the beginning of subatomic particle research. But the atom's secrets didn't stop there. Enter Ernest Rutherford. Rutherford proposed that most of the atom's mass and positive charge is concentrated in a tiny core, which he called the nucleus, while electrons orbit around it like planets around a sun. This was a significant leap from Thomson's plum pudding model, which proposed that electrons were scattered uniformly throughout the atom. Finally, we reach Niels Bohr. Building on Rutherford's model, Bohr proposed that electrons orbit the nucleus in distinct energy levels. This explained why atoms absorb or emit radiation only at specific frequencies. This model, although not entirely accurate, still forms the basis of our modern understanding of atomic structure. From a philosophical idea to a scientific fact, the discovery of atoms is a journey through time. Now that we know about the discovery of atoms, let's delve deeper into their structure. Imagine an atom as a tiny solar system. At the heart of this system we find the nucleus, a dense center containing protons and neutrons. The protons, positively charged particles, are the defining characteristics of an atom. They give the atom its identity. For instance, an atom with one proton is hydrogen, while an atom with two protons is helium. This number of protons is what we call the atomic number, and it is this number that determines the identity of the element. Neutrons, on the other hand, carry no charge. They are neutral particles, hence the name. They contribute to the mass of an atom but do not affect the atomic number. The combined number of protons and neutrons is known as the atomic mass. Surrounding this nucleus we find electrons. These are negatively charged particles that orbit the nucleus in a cloud-like formation. They move in energy levels or shells, which can hold a specific number of electrons. The first shell can hold 2 electrons, the second 8, and so on. The interaction of these protons, neutrons, and electrons creates a delicate balance. The number of protons usually equals the number of electrons, creating a neutral charge. But when this balance is disrupted, we get ions. Ions are atoms that have gained or lost electrons and therefore carry a charge. Atoms are like the building blocks of matter. They combine in countless ways to create everything we see and touch. But despite their tiny size, atoms are far from simple. They are complex systems with their own rules and behaviors. The atom, then, is a microcosm of the universe. It is a perfect example of how complexity can arise from simplicity. Each atom is a testament to the beauty of nature and the intricacy of the physical world. The structure of an atom, as tiny as it is incredibly complex and fascinating. Atoms don't exist in isolation, do they? They interact, they combine, and they form the world as we know it. So let's dive in to understand how these tiny particles interact to create the vast diversity of matter that we see around us. Atoms are like social butterflies of the microscopic world. They hate being alone and are always looking to connect with others. This connection, or bond, forms the basis of every material in the universe, from the air we breathe to the ground we walk on. This bonding is not random, though. Atoms follow a set of rules when they interact, much like a complex dance. At the core of these interactions is the concept of electron sharing or transfer. You see, atoms strive for stability, and they achieve this by having a full set of electrons in their outermost shell, often called the valence shell. When atoms come together, they assess the situation. If one atom has an extra electron and another is one electron short, voila, a transfer occurs. This is known as an ionic bond. Salt, or sodium chloride, is a great example of this. Sodium has one extra electron, while chlorine is one short. So sodium happily hands over its extra electron to chlorine and they form a bond, creating the salt that flavors our food. But what if both atoms have room for more electrons? Well, in that case, they decide to share. This sharing of electrons results in what we call a covalent bond. Water, or H2O, is a classic example of covalent bonding. Each hydrogen atom shares its single electron with oxygen, which needs two more to reach stability. So, two hydrogen atoms team up with one oxygen atom to form a water molecule. These interactions, these bonds, are the basis of chemical reactions. They allow atoms to transform, to combine in new ways, creating an endless variety of molecules and compounds. And it all starts with the humble atom, seeking companionship, seeking stability. These tiny atoms, through their interactions, form the basis of life as we know it. So, what have we learned today? We've journeyed through the vast universe within an atom, discovering the fascinating intricacies of these minute particles. We've examined the history of atoms, tracing their discovery back to ancient times, where philosophers like Democritus postulated their existence. We then followed the scientific pursuit through centuries, witnessing the contributions of Dalton, Thomson, Rutherford, and Bohr, each adding a piece to the atomic puzzle. The atom, we learned, is much more than just the smallest unit of matter. It's a microcosm of particles, each with unique properties. Protons, neutrons, and electrons dance together in an intricate ballet, maintaining the balance within the atom. The nucleus, the atom's heart, carries the weight of protons and neutrons, while the electrons orbit in energy levels, creating the atomic structure as we know it. We dove deeper into the atom, examining its interactions. We saw how atoms bond with each other, forming molecules, and how these bonds result in the diverse matter we see around us. Everything from the air we breathe, the water we drink, to the very cells in our bodies is made up of these bonded atoms. We also touched on the importance of understanding atoms across various fields. In chemistry, for instance, atomic theory is fundamental to understanding reactions and molecular formation. In physics, atoms explain the nature of matter and energy. Even in biology, understanding atoms is crucial to comprehend life at the molecular level. As we conclude our journey into the world of atoms, we realize how these minute particles play a colossal role in shaping our universe. The atom, though minuscule, holds immense power. It's the building block of everything we know, dictating the nature of our reality. It's quite a thought, isn't it?